The idea of the Kestrel Wing project was born whenever we reached out to Dr. Ralph Kimberlin, who's a professor at the Ford Institute of Technology, and he had been a test pilot for this particular airplane. He knew it had very interesting, innovative technologies implemented in it, but unfortunately, during the 1970s, when it was originally built, this airplane was handicapped by the technology of the time.
Currently, there is a need for an airfoil configuration that allows for low loiter velocities while still allowing for much higher transonic cruise velocities. And such a design would also be capable of short takeoff and landing capabilities and would be ideal for reconnaissance or military application.
The project objectives for the Kestrel wing include designing a demonstration model for a senior showcase that include an augmenter wing, a main wing, an internal ducting ventilation system, and an electric ducted fan, complemented with a flap system that works in conjunction with the propulsion that is varied. The second project objective is to build a functional experimental wind tunnel test model that utilizes upper surface blowing, an augmenter wing, and a functional flap system. And lastly, to analyze the aerodynamic effects of inducing upper surface blowing, an augmenter wing, and a functional flap system.
The main goals of the propulsion subsystem in the Kestrel wing were to select an engine that's readily available in today's market that could be used in a full-scale example to prove that the technology we're researching is relevant and applicable today. We decided to go with the Rolls-Royce AE3007 engine, which is a very widely used engine in UAVs by the United States military as well as other nations. Based on that, we selected a 90 millimeter electric ducted fan engine to power our demonstration model because it allowed our scaling ratio to be 13:1. One of the biggest challenges for the propulsion subsystem was to figure out how to simulate air being blown over the upper surface of the wing out of our vents without actually having an engine being used. The way we decided to do this and have accurate results was to run a pressure line through the bottom of the wind tunnel test section to the wing.
The vehicle design subsystem used the mission requirements to determine the optimal design for the Kestrel wing. We used carrier-based aircraft as a reference to dimension the wing and its components and scaled those dimensions down to match our selected 90 millimeter electric ducted fan for the demonstration model. The resulting design had a swept wing and augmenter wing directly connected to the engine column. This allowed for a simple connection between the engine and the plenum for blowing over the upper surface of the wing.
The team decided to use Siemens NX as a 3D modeling software, as it is what most of the team is familiar with. On top of that, the software is used in most aerospace companies. Besides NX, data analysis was collected and organized with MATLAB and Excel.
The purpose of the prototype structure subsystem is to take all the constraints given by the other subsystem and to fabricate a display model that will be able to show the upper blown surface wing working in unison with the quantum flap. Some of the fabrication procedures used during the development of the wing was using 6061 sheet aluminum to wrap around the 3D printed augmenter wing in order to decrease the surface roughness. Another procedure we used was laser cutting acrylic to form the ribs for our wind tunnel test model.
The purpose of the aerodynamic analysis subsystem was to perform analysis on the GOE 630 wing with and without the augmenter. And after analysis, we look at the coefficient lift and coefficient of drag values at different angles of attack. The software that we used for this project was ANSYS Fluent, and ANSYS Fluent was our computational fluid dynamics software program. This was used to insert the wing with and without the augmenter, and it was used in the airfoils to calculate coefficient lift and coefficient of drag values. The flow simulation results from ANSYS showed that we got a greater angle of attack at stall when we were implementing the augmented wing. The wind tunnel tests showed that we had an net increase in performance when we had the induced air going through the motor.
To determine the effects of upper surface blowing on the Kestrel wing, we went to the flight test manual for the JW1 jet wing. This allowed us to develop relationships for the lift coefficient to the angle of attack, as well as the lift coefficient to the flap deflection angle.
To recreate the flow data that we collected through ANSYS, a wind tunnel test model was meticulously designed to utilize upper surface blowing technology, an augmenter wing, and a flap system, essentially to recreate an infinite 2D airfoil section of our Kestrel wing technology.